Hi guys. I've been asking you to think about mass and how to define it. And I want to propose a definition for mass in this video and then talk through some of the consequences of that definition. But first, in order to define mass, I want to define force, and that'll be clear why after I do it. So there's sort of three goals for this video. One is to define force. Two is to define mass, and three, based on the definition of mass, an example of how you might measure mass, which can be sort of tricky once we get into it. But first, let's define force. So we've defined force in class, and I want to restate some of those definitions. In class, we said that the most basic definition for a force is a push or a pull. So what does that mean? That means kind of what it sounds like. In some ways, push or pull, those aren't technical terms, but we kind of know them when we see them. So a push is anything that feels like a push, a pull is anything that feels like a pull. Those are forces. So if I lean into the wall, I'm pushing on the wall, that's a force. If I get hit by a rock that someone threw at me, that feels like I'm being pushed by the rock. That's a force. If I feel pulled down by gravity, that's also a force. Gravity is also a force. So anything that's a push or a pull, that's a force. But we also identified that acceleration is caused by force too. But it's not that any force causes an acceleration. So it's not that not all forces cause acceleration. Because imagine a case where I have, let's say, here's a box. It's a mystery box. Don't know what's inside. And I am pushing the box. I'm pushing it really hard. So I'm applying a force on it this way to the right. That's the force of my push. But also on the other side, there's someone else pushing back. So someone who is shorter, but at least as strong. So they're pushing back with the same push. I guess I want those arrows to be the same length-ish. So neither of these forces here are causing an acceleration because those forces are sort of canceling out. And so the total force on the box is zero and there's not acceleration. But we know that forces are associated with acceleration. We saw that when you apply a constant force in lab 10, the motion graphs lab, that the acceleration is also constant. So what we want to say is we want to define both force this way, and we want to define something called net force too. So net force is proportional to acceleration. Proportional, that's how you spell that, to acceleration. So what is net force? Net force is the sum of all forces on an object. So in the example above, the net force here would be zero. Because I've got, if I summed up the forces, I would have a push to the right and a push to the left. If I add up those two forces, I get zero. So the net force is zero, and that's why there's no acceleration. So if you have multiple forces acting on an object, you got to figure out what all of them are doing to the object in order to figure out what the acceleration would be. If there's a single force acting on an object, then that single force will be proportional to the acceleration on the object. And we're going to use that a little bit later on. But these are sort of basic definitions for force. A force is a push or a pull. Anything that seems like a push or a pull is probably a force. Net force is the sum of all forces on an object, and that is proportional to acceleration. Um, we didn't exactly specify the way in which it's proportional to acceleration. We just said that it is. So you push on something and the acceleration you get is proportional to the net force. If the net force is bigger, you get more acceleration. If the net force is smaller, you get less acceleration. All right, so next, now that we have these definitions for force, let's define mass. So let me scroll down here a little bit. So in this section, we're going to try to define mass. So let's do a little thought experiment here. So let's say I have a box sitting on a table. So here's a table. There's a box sitting on it, and it's an empty box. So empty box. And I push on that box. So in other words, I apply a force on that box. There I am, I'm smiling. I'm very happy about this. And I push on this box with some amount of force. So let me call that force F. That box is going to accelerate. So there'll be some acceleration for the box. Let me call it A for the empty box, A sub E. So that box will accelerate. So the thought experiment here is if I take this same setup, so the exact same thing, let me copy it and paste it over here. So I take the same thing, except now I fill the box with rocks. So this box is now full of rocks. Tons of rocks. Lots of rocks in the box. This was not intentional to rhyme this way, but I have rhymed. I think it's okay. The thought experiment we could perform here is to ask, how will this box behave differently than the empty box? And I think that we would all agree just from intuition that the acceleration of the rocks box, A sub R for rocks, will be smaller for sure than for the empty box. So bigger acceleration here for the empty box, smaller acceleration for the box full of rocks. And this difference is, what we'd say is that the box that has rocks in it is heavy. It's heavier, so it's harder to push. If the empty box is light, it's easy to push, so it's easy to make it accelerate quickly, whereas the heavy box is harder to make accelerate. And this is really what we're talking about when we're talking about mass. We're talking about how hard is it to accelerate something. So mass is a measure of how hard it is to accelerate something. Oops, that looks like an E. This sometimes is called inertia. So this is sometimes called inertia, which really means the same thing as what I just wrote here. But this could be a new word for you, inertia. So inertia is resistance to changes in motion or resistance to acceleration. And that's what we mean when we say mass. Mass is how difficult it is to accelerate something. If something has more mass, it is more difficult to accelerate. And this is the feeling of heaviness that we all intuitively understand as mass. When you try to push on something that's heavy, it is hard to push. That's the most basic statement of mass. But how do we define this mathematically? We can. We defined force sort of mathematically. We said that force was proportional to the acceleration on an object. So in the above case, if we look at these two cases right here, so the empty box case and the rocks case, those two cases, it's the same force in both cases. let's say I'm applying F here on the empty box and applying F here on the full box. The force is the same, but I get different accelerations. So the force by itself can't be the whole story of how how the acceleration works. I also need to know how much mass the box has. In this case, I've got less mass, so I got more acceleration. In the heavy rocks box case, I've got more mass, so I've got less acceleration. And this is how we define mass. Mass is defined as a ratio of net force to acceleration. This is a definition for mass. You may have seen this equation before in its more famous form. So the more famous form of this equation is this: F equals ma, which is just a rearranged version of this equation I just boxed. So if mass is equal to net force over acceleration, then force is equal to mass times acceleration. F equals ma. It's usually written F equals ma, but what the F means here is net force. So the net force on an object is equal to that object's mass times its acceleration. The important thing to emphasize about this equation is that it is not empirical. Often you'll hear this also called Newton's second law. This is Newton's second law. And we'll use this a lot more. It's different than a lot of the other results that we've seen this year. Mostly the other equations that we've come up with are empirical, and we've derived them through our lab work. But this is not an equation that you can derive through lab work. It's a definition of both mass and force. What force means is based on mass. What mass means is based on force. And that poses some pretty big challenges in measurement, which I want to talk about in the next section here. Okay, so the last thing that I would like to talk about here is how to measure mass given these definitions for force and mass that we've just talked about. So the definitions that we're talking about are net force equals ma, Newton's second law, or the way I originally stated it as mass as being defined as a ratio of net force to acceleration. So mass is, for a given amount of force, telling you something about how much acceleration you're going to get for that amount of force. If mass is big, you get less acceleration for the same amount of force. And that's the kind of intuitive feel we have for what mass is. So that's fine. If we want to actually measure mass, this turns out to be a little bit harder than it seems. Part of measuring mass is pretty straightforward, because part of measuring mass is figuring out what acceleration is. And we know how to do that. So we know that acceleration is just a change in velocity over a change in time. I guess this is an average acceleration, to be a little bit careful here. But in a lot of cases, we were dealing with a constant acceleration and a constant force. So let's say if we did have a constant acceleration, we would know how to measure it. We would just measure velocity at two different times and then take this relationship here. So we'd measure, say, the velocity at some final point minus the velocity at some initial point, and then divide that by the difference in time between those two velocities. And we know how to do that. The units of this, we know too. The units of acceleration are meter per second per second. Meters per second per second. So the change in velocity, meters per second, over time per second. Okay, so that part's fine. However, We have defined what force is and we've defined what net force is, but we haven't really talked about how to measure that. How do you quantify what a force is? It seems like if you were going to measure mass, you would want to quantify what the force is. So let me set something up for you here. So I've got two cars that I've drawn on the screen, and I've put fans on them. So there's a fan here. Just like when we did Lab 10, we put the fans on the cars, we let the fans blow, and the fans pushed the cars forward. So the fan blades push against the air pushes back against the fan blades, and that supplies a force on the car. And I've called that force F here. So I turn the fan on, it pushes the car with a force F, and I've given the car some mass. So this car on the left has mass M1, and this car on the right has mass M2. And you can see from the way I've drawn the cars that car 2 is a little bit bigger than car 1. So let's maybe presume that mass 2 is greater than mass 1, although that's not necessarily the most important thing about this setup. We'll just work with that assumption. So how would I measure mass here? Well, if I could use this equation, if I could measure force and acceleration. So in this case, if we assume that there's no friction, for car 1, if I let the fan push the car with force F, and I measure the acceleration of the car as it goes. So maybe I set up photo gates and I measure acceleration the way that we have measured acceleration before. And I take a ratio of those two things. The force divided by the acceleration of car 1 would be equal to the mass of car 1. I can measure acceleration, but I don't know how to measure force. I don't know how to quantify that. I know that there is a force, but I don't know how to quantify it. So this method by itself doesn't really get me anywhere. I could do the same thing for car 2. So if I had this value of the force that the fan supplies, which if it's the same fan will be the same force. And let's say that it is the same fan. So I'm pushing car 2 with the same force. And if I set up photo gates and measure the acceleration of car 2 as it went along the track, maybe that's A2, that ratio would get me M2. But again, I don't know the force, and that's a problem. So there, right away, here's the problem with our definition for mass, is that if we want to measure mass, we need to know how to measure force, and we don't know how to do that. There's a little bit of a workaround here, though, which is that if what I have tried to do here, when I have written these equations, this one, M1 equals F over A1, and M2 equals F over A2, those are ways to try to figure out the absolute value of the mass. If I had a value for F and a value of A, I could get a numerical value for M1 and M2, which would be the absolute value of the mass. But I can't do that because I don't know F. So let me write it this way. I can't get an absolute value for M1 or M2 that is a numerical value. I'll put the parenthesis down here because I don't know F. However, I can get a relative value for M1 and M2. And let me tell you what I mean. So what I do know, though, is that F is the same in both cases. If I use the same fan, I'm applying the same force on both cars. And I can use that fact. So what I do know is that F is equal to M1 times A1. And also F is equal to M2 times A2. Those two things are the same. So I can get a relationship between M1 and A2. Between M1 and M2. So I know that F is equal to M1 A1, but it's also equal to M2 A2. So what if I wanted to get M2? Well, I know then that M1 times A1 over A2 is equal to M2. So let me put numbers to the situation. Let's say that I push on both, I have the fan on both cars, I let them run, I measure their accelerations, and I measure that A1, when I let the car be pushed by the fan, is equal to 2.5 meters per second per second. When I push car 2, which is a little bit bigger, a little bit more massive, when I push car 2 with the same fan, it accelerates at 1.5 meters per second per second. So a little bit more massive means a little bit less acceleration. And what this tells me is that M1 times 2.5 over 1.5 is equal to M2. So 2.5 over 1.5 is about 1.66. So M1 times 1.66 is equal to M2. So this does not tell me what M2 or M1 actually is. I don't know if M1 is 1 kilogram or 2 kilogram or 3 kilograms or whatever it is, but it does tell me that no matter what M1 is, M2 is 1.66 times that value. So if M1 was 1 kilogram, for example, M2 would be 1.66 kilograms. That's a statement of relative mass rather than a statement of absolute mass. I don't know what M2 and M1 are, but I do know what they are relative to each other. So this is a relative statement of mass. So if let me box that and say that. So this is a relative measurement of mass. And in some respects, this is the best I can do with this definition of force and mass that I have, because I don't know how to measure force. I don't know how to quantify force. So given that, a relative measurement of mass is kind of the best that I can do. On the other hand, we do know that we talk about the actual numerical masses of things all the time. It makes perfect sense to say that something has a mass of 1 kilogram or 1.3 kilograms, or, you know, my mass is 70 kilograms or whatever it is. And so we know we can do that. So let me explain how we do that. We sort of play a trick, and let me explain how that works. So if I scroll down here, let me redraw my cars. So here's a car, here's car 1. Car 1, and it had a fan on it, had wheels, and we measured that car's acceleration. And we had car 2. Here's car 2. Car 2 is a little bit more massive. We know it's 1.66 times as massive as car 1, at least if we count the fan too. But what we do is we just define something to be 1 in our units of mass. And whatever those units are, that's just the units that we then stick with. So what I could do is I could say, I'm going to define the mass of car 1 to be 1 Hlt of mass. And this is by definition. And what I mean by definition is I have just stated that this is true. This is just an arbitrary thing that I have now made true about the world. Now everything, every mass that I measure can be in terms of Helts. And what 1 Helt means is the mass of car 1. That means that now I can actually measure the mass of car 2, because I know that the mass of car 1 times 1.66 is the mass of car 2. So now the mass of car 2 is 1.66 Helts. And that's now based on the definition of what 1 Helt is. And I can always refer to the definition of what 1 Helt is when talking about the mass of anything else. So in this system, probably I weigh a couple of hundred Helts now, and probably the mass of the Earth is like, you know, many, 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 many Helts. But it's not going to be that much different than the system we have now. So this then gets to, like, what are we talking about when we talk about a kilogram? Kilogram is the common measurement for mass that we all use. So where I would like to finish here in this video is what is a kilogram? In this silly little example that I just made, a helt is car 1. But what a kilogram is a cylinder of metal, or at least it was this till very recently, and we can talk about why and how it changed. But for a couple hundred years, 1 kilogram was defined as a cylinder of metal that they kept in a basement in France. The reason why they kept it in the basement is so that nothing would happen to it. They tried to keep it safe. They put it in a bell jar that had all the air pumped out so air wouldn't interact with it. They kept it in a dark room so light wouldn't interact with it to keep it as steady and stable as possible. This thing was called the International Prototype Kilogram. International Prototype Kilogram. And this is the thing that was 1 kilogram, sometimes called the IPK. IPK for short. So what that meant is this was the thing that was 1 kilogram, and every other thing in the universe was measured relative to this. So if I do the test that I just proposed with these cars, but with this International Prototype Kilogram, I push this IPK with some force, I measure the acceleration of the IPK, and then I can do the same test with another object and see how the other object's acceleration compares to the IPK's acceleration. Then I can define, or I can measure the mass of any other object. That's how I do it. That's the workaround for this ability only to measure relative mass. You just define something to be 1, and then everything else falls into place. Another thing that I want to point out about this is we said before that we didn't know how to measure force, but now we do, because if I take the IPK, here's the IPK, and let's say I push it on a frictionless surface, which they probably won't let you do, but here's the IPK. If I push it with some force and I measure the acceleration of the IPK, then I just multiply by 1, whatever the acceleration is, I multiply by 1, and that's how much force I'm applying on the IPK. So by defining the mass to be something, then now I can start quantifying forces and talking about quantities of forces, which is kind of cool. So for example, if I push on the IPK with some force, and I find out that the acceleration of the IPK when subjected to that force is 1 meter per second, then the force on the IPK is equal to mass times acceleration. So 1 kilogram by definition times 1 meter per second, that's the acceleration. So the force is now 1 unit of force. And what's the units of force? 1 kilogram times meters per second. So kilogram meter per second squared. That's the unit of force that I have. And we call that unit a Newton. 1 Newton. So a Newton, that unit is equal to kilogram meter per second squared. Those are the units that I use. So once you define something to be 1 unit of mass, then you can start quantifying force, and the units of force that we have are based on the units of mass that we have. So force isn't a fundamental thing. What's fundamental is this unit of mass that we've defined, and then force is based on that. So the definition for mass that we have, or for force and mass, F equals ma, it's circular. So mass and force are defined together, and in order to get force, you need to define mass, or vice versa. If you wanted to, you could do the other way, where you define force to be something, you define a unit force, and then you can base your mass off of that, but that's not the world that we live in. We have defined mass and then base force on that. This is kind of a big idea. A lot of units work this way. So for example, when you talk about length measurements, what's a foot? Well, uh, what a foot used to be was literally the size of the king's foot. And then all length measurements were based on that. But it was just a standard measurement meant to standardize things. So you had something to compare length measurements to, and then to say that, this building is 30 feet wide by 50 feet long. And everyone knew what you meant when you said a foot. And it's kind of the same thing here with the IPK. What is 1 kilogram? It's this specific thing, and then we can compare everything to that. Um, that's more or less how our system of measurement works, which is really interesting and kind of hard to wrap your head around. So I'm happy to keep talking about this. If you think that I've just made all of this up and it can't possibly work like this, I um, I, I I I don't think that you're wrong exactly, like not wrong in an abstract sense, but this is the way it works. So we'll keep talking about it, and let me know if you have any questions, and I will see you soon. Bye.